All right, guys, I'm going to get started. So I'm going to talk about Apache Tez, which is a new, relatively new compute framework on top of Hadoop. Quick introduction, I'm Siddharth Seth. I work as an engineer at Hortonworks. I've been working on Hadoop for about 3 years now, Yarn and MapReduce in the past, and of late on Tez. So just getting started, an outline of what I'm going to cover today. First up is the motivation for Tez, some of the limitations of MapReduce and why we decided to build Tez. A quick introduction on Tez, how users interact with Tez in terms of API and deployment, the components in Tez and some of the features in Tez, and what the current status of the project is and what's coming up next. So some of the limitations of MapReduce, which is why we built Tez. So MapReduce was primarily built it was very good at doing batch processing. It's been around for 6 years, 7 years, and it's done very well at batch processing large-scale data. It does, however, have limitations. So you can only execute two-stage plans. You have it's a map followed by a reduce. There's nothing else that you can do. The way data flows between the map and the reduce is fixed. It's always sorted and partitioned and then sent over to the reducer from the mapper. And since it was primarily geared towards batch processing, there wasn't really a lot of incentive to remove a lot of the overheads. When you're running jobs which take minutes, a few seconds don't matter that much. So downstream systems like Pig and Hive and cascading, their plans will typically be a graph. So these plans are forced onto MapReduce. They're converted to run on MapReduce since that's what was available. But it's not the native best fit in terms of execution. Also, the shuffle, which is the sort and partition, isn't always required for all operations which are done by these systems like Pig and Hive. That's where Tez comes in. So Tez itself it's a compute platform. It's distributed. It has fairly low-level APIs, which I'll talk about at a later point. It runs on top of Yarn, which means all of the scheduling capabilities and multi-tenancy capabilities that Yarn provides in terms of queues, multiple users, all of that comes in. The computation itself is expressed as a DAG. So MapReduce at this point just becomes a subset, a two-stage DAG with a certain connection pattern. We're targeting both interactive queries as well as batch processing. So Tez will be able to do what MapReduce did, and at the same time, it will be able to execute jobs much faster. The system is highly pluggable. So Tez it provides several points where you can plug in, which is the connections between various vertices, controlling the vertices itself in terms of scheduling, and the inputs and outputs itself can be configured. So this is just a sample of what a Pig script or a Hive job would look like on MR versus Tez. So on MapReduce, you end up. So the right side, which is Tez, is much closer to what a Hive or Pig plan would look like before it's converted into the actual execution platform. In Tez, it gets converted directly, since it's almost a 1:1 match. In MapReduce, you end up taking this plan, converting it into about four MapReduce jobs. There's a lot of unnecessary steps like persisting data to HDFS, reading back the same data, which is all avoided in Tez. And there's more detail on this at a later point. So this is just a sample DAG, this is TPCDS, the benchmark query set, query 18 on that, on Hive running that query on Tez. It's a fairly complicated query, ends up running about 10 vertices or so. This runs as a single DAG job on Hive. On MapReduce, this would run as closer to about 8 or 9 different MapReduce jobs with data being persisted to HDFS unnecessarily throughout. different connection patterns, so scatter gather, and I'll talk more about those later as well. But scatter gather and broadcast is used in this, which was not possible in MapReduce. So the user interaction itself, there's two components to Tez. There's the DAG API, which is used to construct the actual DAG, the DAG definition. And then there's a runtime library, which is a bunch of components which can be reused to form actual tasks or processors. The DAG API is used to define a DAG at a logical level. So you're not defining the actual physical DAG, you're just defining connections. So the diagram on the right top is what a logical graph looks like. You're just saying these vertices are connected in a certain manner. How it's going to materialize at runtime, how it's going to materialize will be determined at runtime. So along with specifying the logical DAG, you specify parameters on what the JVM looks like, the size of the JVM, any other options, any resources which may be needed to run these tasks when deployed on the cluster. And so the DAG is built basically of vertices and edges. A vertex is where you define processing, which is how the data is going to be manipulated. On the edge, you define how data is going to move between various vertices. So there's different connection patterns, scatter gather, one-to-one. There's a bunch of others, which can be used to specify how data is actually going to move. And the edge is also used to specify the actual runtime components which are going to be used. You also specify parallelism while building the DAG, but this is something which can be overridden at runtime. In several cases, it is actually determined at runtime. So the runtime library basically has three APIs. There's an input, a processor, and an output. A processor is where the actual compute happens. An input is the data source, and you can also define properties on whether the data is going to be sorted or partitioned or merged together. An output, again, is a data sink. You define whether it's going to generate partitioned output, whether it's going to sort the data, whether it's just grouping and not doing any sort at all. And a task is actually built by combining multiple inputs connected to a single processor, and that processor can generate output to multiple outputs. So in terms of the runtime library, our end goal is to have a set of reusable inputs and outputs, which can be used by various downstream projects or Tez consumers. Processors, not so much. Typically, processors will be written by the downstream project. So as an example here, we have, if you want to run MapReduce on Tez, we have the equivalent of a mapper in MapReduce, which is a processor connected to an MR input and writing output to a file-sorted output. The reduce is the middle diagram where it's reading shuffled input, which is typically connected to a file-sorted output on the providing side, and generates data out to HDFS. So once you combine this, an MR mapper and an MR reducer, you get the equivalent of MapReduce. Then you can have custom tasks. This is an example of a join processor, which is reading from two HDFS inputs and writing out sorted output. The processor, again, is custom at this point. So the pieces which are available in the runtime library right now are a sorted input and output pair. These are file-based. An unsorted or unordered input and output pair, which are again file-based, and MR input and MR output, which are wrappers around the file input format and file output format. They let you read data which is already residing on a file system, typically HDFS. So an example of how these can be used to construct various joins is, so your sort merge join is just sorted output going to shuffle input. This is very similar to what a reduce looks like, a map to reduce connection looks like. For hash joins, you don't actually need any sorting. So you just write data out unsorted, read it in, and construct a hash table or however you want to do the join. Then you have a dynamically partitioned hash join where the same output can be used, but you will it's going to partition data on the fly. It's not generating all of the data up front, it's partitioning the data. So in terms of low-level APIs, so Tez is trying not to enforce any constraints on the type of data. We're not saying that you have to use key-value pairs or you have to use a specific serialization mechanism or a specific configuration mechanism. That's all left up to the users. So in a lot of cases for Pig and Hive, it makes sense to just use tuples and not key-value pairs. It's wasteful to use key-value pairs. They're absolutely free to do that. In terms of configuration, the serialization mechanisms, again, Tez doesn't provide anything. All of our APIs accept a byte array as the configuration parameter. It's up to the users to serialize however they want to configure their tasks or inputs or outputs. It's up to the users to specify, to serialize that into a byte array provided to us, and then in the actual input and output, deserialize it and process it. Tez will never interpret this data. Tez will never try to do anything with this byte payload. It will, however, be available to all the plugins that you write. So the various pieces of Tez which are pluggable, and at that point, you can actually interpret this and do something useful with it. On the deploy side, it's fairly straightforward. We've tried to simplify this. You don't need to put anything on the cluster. It's completely a client-side deploy. You put the Tez libraries onto a file system, typically HDFS, which is accessible on the cluster. And after that, the Tez client takes care of making sure that these libraries are available wherever the task actually executes. So that happens via the Yarn distributed cache. And it's possible to have multiple versions of Tez on the same cluster. So in terms of development or debugging, that makes it a lot easier. So what we typically have is a single version, which is a stable version running on the cluster. And anytime we have a patch or we're trying something new, we just sideload another version via the client only without affecting the actual deployment on the cluster. So some details. So this is what a Tez application looks like when running on Yarn. So anyone who's familiar with MapReduce, this should be, they should know what this is. There's a client which talks to Yarn to launch the actual application master. This is where all the details on what resources are required in the cluster, all of that is passed in. Once Yarn launches the AM, the client interacts directly with the AM to submit DAGs to it. So this is slightly different because Tez can do multiple jobs or multiple DAGs per AM, which MapReduce cannot. The AM itself, at that point, will process the DAG, figure out what kind of containers are required to run tasks, talk to Yarn, get these containers, and launch the actual tasks on the node manager. So the AM, which is the DAGAppMaster, is pretty much the central coordination point. It takes care of the actual scheduling of vertices. So it has to make sure that producing vertices are complete before consumers start running. Within a vertex itself, it does scheduling based on, so there's this concept of slow start in MapReduce. And Tez can do the same thing by having scheduling at the vertex level. That's also pluggable, which means users can actually go and customize the scheduling. And finally, we have the task level scheduling, which is locality aware, takes care of reuse, reusing containers, and this is the piece which actually talks to Yarn to get more resources when required. The AM is also responsible for fault tolerance. So if a node goes down, for example, the AM will actually figure out which of the tasks ran on this node. It will go back and rerun the relevant tasks, depending on who needs data from, depending on what needs to execute at the final level. The AM figures out what all needs to be redone at a higher level. Recovery comes in the sense when the machine running the AM itself dies, for example. At that point, Yarn would relaunch the AM, and we would continue the processing from where the previous AM left off. So we checkpoint at various points, and the new AM just continues from that point forward. So the last four are really pluggable pieces within the AM, which is there's a plugin for writing input initializers, for output finalizers, routing, custom routing, and which is managed via Vertex and Edge plugins. Vertex plugins also give you the ability to do custom scheduling. if you require. If you need to schedule a task based on how many tasks upstream have completed or based on some other criteria, that's where a Vertex Edge plugin comes in. Input initializers are used, for example, generating initial splits. That happens via an input initializer. Output finalization is where something like an MR output committer runs. And again, this is all pluggable. Users can specify whatever it is they want to run. Containers is where the actual execution happens. So containers and Tez have a separate lifecycle of their own. Once a container is started up, Tez assigns tasks to these containers. We end up reusing the container for several different tasks. It has something called the object registry, which can be used by these tasks to cache data between stages or between different DAGs if required. The container also takes care of, so since we reuse these containers across DAGs, potentially across DAGs, these containers take care of relocalizing resources, adding them to the class path, handling additional tokens in terms of security for a newly submitted DAG. So how the actual data flow coordination happens in Tez is, so the AM takes part in how events or how the data is to be routed. A producer task, in this case the green box, it writes its output out either to physical memory or to disk or HDFS or any source, any destination. After this, it informs the AM about where it generates this event called a data movement event, which has information about where this data has been written out. Now this data movement event contains a byte payload. We are not saying we know how to understand where you're generating data. The AM will not look at that byte payload at all. All it does at this point is say that this is where the edge router kicks in. And these edge routers can be configured by users if you want custom scheduling. This is where the edge router kicks in and actually sends the same event down to the consumers. The consumers need to interpret the byte payload to figure out where the actual data is and then fetch the data directly. So it's just the meta information which is being managed via the AM. The actual data flow happens directly between wherever the producer wrote the output and the consumer consumes. Has to pull it from there. So the data movement patterns, so MapReduce, so the one on the left is scatter gather. That's pretty much equivalent to a MapReduce shuffle. That's where you write sorted, partitioned output. But the same pattern, scatter gather, can be used for unsorted data as well if required. One-to-one is another one which is predefined in Tez, where the producer and consumer have to have the same number of tasks, and there's a direct connection between them. So this is useful when, for example, you're doing hash joins, and there's multiple tables to join with, but all these tables together don't fit in memory, but individually can fit in memory, in which case you would just process one row at a time and forward it to the next one. Load the next table. The hash table is loaded in subsequent tasks. You just pipeline it all the way through. The last one, which is predefined, is broadcast, where all of the data generated by a task is sent to all of the consumers. So one producer generates some data, and that's sent to all of the consumers. This is used for, in terms of joins, this is used for hash joins. Then you can have custom routing. This is where the plugins come in. And the three which I mentioned there, scatter gather, one-to-one, and broadcast, actually use the same plugin mechanism. They're just implemented as plugins within Tez. There's nothing special happening there. They're just predefined. All right, so this is an example of how a plugin works. So this is a bucket. So Hive actually makes use of this for doing bucketed map joins. So you have a pre-partitioned fact table, with 3 partitions or 3 buckets. That will initially be run through the input initializer to determine how many tasks are actually being run. So in this case, the first partition runs a single task. The second partition is running 3 tasks. The last one is running 2 tasks. Once it determines all of this, it sets up the routing table or sets up the edge to actually route the events correctly. The other side of the join, the other table on the join, need not be partitioned. Once it starts reading the data, it could do some filtering, any other processing. When it's generating its output, it needs to partition that output. So it's going to generate some output for the 3 partitions which exist in this case. The Edge plugin, because of the routing table having been set up properly, will make sure that this data actually moves to the correct destination. So in this case especially, all of the data generated on partition 2 by the source tasks will be sent to each of the downstream consuming tasks. So this doesn't, the same for partition 3. This doesn't fit into any of the pre-existing connection patterns like scatter-gather or one-to-one. It is a custom routing table which is set up based using these plugins. So what this also allows, in case of Hive on MapReduce, what used to happen in case of bucketed map joins is that a single bucket would only ever be processed by a single task, and you needed both sides to be partitioned. You needed both sides to be pre-bucketed. With Tez, you can increase the parallelism. That's like, for example, the 3 tasks running partition 2. In case of MR, that would only ever have been a single task. And you can dynamically partition the other side. You don't need both sides to be partitioned. You can actually even dynamically partition both sides of this join if you really want to. And I think Hive is going to move to that at some point. So in terms of performance improvements that we've made with Tez, so first is the direct wins over MapReduce. We eliminate all of the writes, unnecessary writes between jobs. So HDFS writes, as well as unnecessary data reads, completely go away. All of that happens directly over the network. So when you're running a complicated or even a simple Hive query or a pig script, it'll typically have more than one MapReduce job. What can happen at that point is someone comes and submits a job while the first one is processing, in which case the second job will lose its place in the queue. That doesn't happen with Tez. We start a single DAG, we get resources for it, we'll reuse those resources all the way through. So you will never end up in a situation where you have got some resources when you started the query, but you don't have the resources anymore during the query execution. That's when the second query starts up in case of MapReduce. And of course, all the additional connection patterns allows Hive and Pig to use unsorted data when they really need to, which is not possible at the moment in MapReduce. So in terms of resource management, Tez reuses yarn containers extensively. We'll go and get a container up front, and then the same container is going to be reused for different tasks running in a particular vertex, for tasks running across vertices, and with sessions, which I'll talk about, tasks running across different DAGs, which means we get rid of all the overhead of talking to yarn, trying to allocate new containers, the launch cost for the actual containers, which is fairly high. And the containers, like I'd mentioned, have this entity called the object registry, which can be used to cache data like a hash table, which you may have built for a task, which can be reused by the next task on the same vertex. Sessions is something which has actually helped us quite a bit. What we do here is a session is effectively a connection between the client and the cluster. And what this lets you do is submit multiple DAGs to the same connection, to the same session. We hold on to containers between DAGs so that the entire launch cost, as well as the time it takes for the JIT to kick in, all of that goes away. And we've seen with experiments that JIT and the launch cost actually contribute in a fairly big way, especially when you care about interactive queries. So what happens here is, once a DAG completes, we're not going to give up the containers. We keep the containers around. And when another DAG is submitted to the same session, the same set of containers is going to be reused. They've already been localized, they've been launched. If it's multiple Hive queries, the JIT has kicked in, and new queries which come in execute very fast. So we've seen queries which run in less than a second where the data processing is not too much. So this does have a side effect that we may end up retaining containers for too long, which means we're eating up cluster capacity, which we don't really have to. So we do release these containers when the session is idle for a while. So when setting up a DAG, you can either set parallelism for tasks up front, or in several cases, it's actually determined at runtime. So in this case, when you're reading your initial input from HDFS, how this works with MapReduce is you generate splits, and these splits are potentially grouped together based on a predefined configuration saying my minimum size is so much and my maximum size is so much. It never takes into account the size of the cluster, what the available resources are, and typically users will never do this. Users will not bother with actually setting this up. In Tez, firstly, it's not done in the client. This entire computation is moved into the cluster itself in the AM. The AM, while doing this in the AM, you have access to the available resources on the cluster. And based on that, Tez figures out how many splits, how to group the splits together, actually. The initial splits will be the same. Tez figure out how to group the splits together based on locality and based on the available resources. And what we try to do is generate about a little over 1x the available cluster capacity, so that in case you have stragglers, the smaller task will run at the end and will run at the same time that a straggler is running. There'll be some overlap between the straggler and the smaller tasks. So this is another problem which used to exist in MapReduce, where the number of reduces is something that the framework would never figure out for you. You'd have to set this up front. Hive and Pig, I believe, do this based on some statistics and some guesses as to how much data the mappers are generating. So Tez makes this far more optimal by where you can actually write plugins which set this at runtime. So what happens here is you'll run all of your mappers, or you'll run a certain set of your mappers, say 80%. Based on that, these mappers report back to the AM, report back to a plugin running in the AM about the size of the data that they've generated. Based on that, this plugin can actually go and set the number of tasks. So you may start off in a situation where you're running 100 tasks. You set 100 reducers up front. The amount of data generated by each of the mappers is fairly small. And at that point, this plugin kicks in and says, I can actually run far fewer reducers. Brings it down to, in this example, brings it down to 10. And the partitions, they look at all of the data generated in each partition and split the partitions across these reducers so that each of them have roughly the same amount of data to work with. So this can be useful in case of skews as well, where a partition is overly skewed, and a reduced task in that case would get only one partition. The less skewed data would go to, so 19 of the other partitions would go to another task. So overall, since we end up writing far less data to HDFS between stages, the name node pressure goes down. We're reusing containers, which means a lot of time spent actually obtaining containers, launching them. All of that goes away. So you should see an improvement in cluster resource utilization. And since we're not doing replicated HDFS writes, unnecessary replicated HDFS writes, the network utilization also goes down. So how Hive is making use of Tez, for one thing, like I mentioned, Hive's native execution plan can pretty much map 1:1 to Tez. They can do multiple different join strategies. So they're making use of broadcast joins. They've moved a lot of their compute into the cluster instead of doing it on the client. And so some of that is, for example, like I mentioned, the split generation is moved into the cluster. Otherwise, you would be limited to so what happens otherwise is if you're doing everything on the client, for one thing, the parallelism is much lower. You can't, if you have a large amount of data, you're processing all of it on the client itself. If you have multiple users using the system at the same point, again, this one client machine can get overloaded. So all of that processing, the initial filtering, split generation has all moved into the cluster. Some numbers on Hive 12 versus Hive on Tez. This is queries from the TPCDS dataset. There's a significant improvement. We have several queries running under 10 seconds. If you simplify queries further, we do have queries which run in less than a second. So this is just an example of where we save some of this time. So this is the same query executing, a fairly simple query running on both MapReduce and Tez. In case of MapReduce, you'll initially have a step to filter and generate these dimension tables, these tables which will be used for a hash join. In case of MR, that is all done client-side, and then pushed to HDFS. For Tez, this initial filtering is actually split across multiple tasks within the cluster itself. After that, most of the changes are in terms of the data being written out to HDFS in MapReduce, and the multiple jobs which it's executing, versus in Tez, the data just flowing directly throughout the system, without sorts, without sorts where possible. So the current status of Tez, we started about, I think, less than a year ago. We have about 3 releases out. The third one is actually being voted on right now. There's about 1,000 JIRAs, of which 700 have been resolved. We've tested it on fairly large clusters, several hundred nodes, with all of our standard test suits for MR, for Hive, for Tez itself, a new test for Tez. We're also running a large set of queries on varying data sets to make sure things work correctly. So Tez is also, so Cascade is also starting to adopt Tez. The Pig adoption of Tez is well underway. They've got all of their basic operations working. They've got all of their basic joins working. At this point, they are focusing on improving performance further. So right now, they've just got it functional, and they're focusing on performance. What they see at the moment is about a 1.5x to 3x improvement in performance on fairly long-running queries, where the query could run for tens of minutes or longer. And going forward, they should see more once they focus on performance itself. So Tez is already, so MapReduce is just a subset of Tez. And we already have a mechanism where you can run MapReduce jobs on Tez. MapReduce has this concept of running on different frameworks. We've got a plugin where we've written a plugin for a framework where you can actually run your MapReduce jobs on Tez directly. It won't get a lot of the performance benefits of sessions because it doesn't make use of those. But the job will run through, as it did on MapReduce. So some highlights from the recent release: we support Hadoop security. A fair amount of work has gone into fault tolerance and recovery, which is, again, very important when you're trying to run long-running queries or long-running jobs. MapReduce has that built in. When you're running on large clusters, there's a good chance that a node may go down, or there'll be a network glitch, or something else goes wrong. So for longer running jobs, the fault tolerance and recovery is actually very important. And of course, stability improvements and bug fixes have gone into this release. This is the 0.3 and 0.4 release. What's coming up in Tez? We've got support for co-scheduling. So what that basically means is, right now, all of our inputs and outputs are based on files, writing data out to an actual file system. The moment you want to start streaming data between these inputs and outputs, you require that both sides to be up and running for that to actually work. So that's where co-scheduling comes in. Once co-scheduling is in, we should be able to stream data through. So another problem which we will solve soon is that if you're running a really complicated DAG, and a long-running DAG, if a node goes down, we do have fault tolerance in the sense that we will go back and rerun the relevant vertices which are required by the currently running vertex. But that's not always the best thing. If the DAG is fairly complicated, you could go very high up in the DAG to rerun. So what we want to do over here is, after a complicated processing stage, or after a stage which takes a fair amount of time to compute, we actually persist data to HDFS, so that becomes a checkpoint in terms of where we want to go back to. At that point, we don't actually need to rerun all the way up in the DAG, but we can stop at this checkpoint. In terms of performance improvements, the scheduling is going to improve with affinity-based scheduling. So where this comes in, for example, is when you cache data. Certain tasks may be able to make use of a specific piece of cached information, others may not. And once these tasks should be able to tell us what they require, as well as what is available on a container. And based on that, based on the affinity there, the scheduler will assign tasks appropriately. For non-blocking operations like unordered reads and writes, we plan to pipeline the movement of data between the producer and the consumer. So right now we wait for the producer to finish producing all data and then move it over to the consumer. For non-blocking operations, it's possible to just, as a producer is producing data, you pipeline that along with the movement of data. So it just overlaps. So the APIs right now are fairly difficult to use. They're fairly complicated and fairly difficult to use. That's something we want to focus on. So we know that Pig uses Tez, Hive uses Tez, Cascading is getting on board. In the summit, we found out that there are several other people who have just started playing with Tez. And yeah, considering there's others who are getting started, I think the API simplification is going to get more priority. We don't want to be breaking APIs forever. We're also moving towards modifying the graph at runtime. This isn't possible right now, but it should in the future be possible to add vertices on an already running graph. And of course, we'll keep focusing on stability improvements. So this is primarily links if anyone is interested in the mailing lists and the Jira system, as well as the source code. Of course, users, contributors, welcome. The mailing lists, we're fairly responsive on them, so feel free to send a mail and contribute. So, yeah, I'm just going to leave this up there. I'm done at this point. Questions? Thank you for listening. Equivalent to speculation. No, speculation is another thing which we are going to build soon. We don't have it yet.
You mentioned about serialization and serialization, just very outside the framework. But for example, would Tez right now be able to process Hadoop or some other kind of more structured hierarchy code in inputs?
So Tez is not enforcing any structure on the inputs or outputs. Pardon? It's not enforcing any structure. So what you would have to do for that is to write an input and output. You'd use the Tez mechanisms to transfer the data over, and after that you interpret that data however you want to. Pardon? Okay. Mm-hmm.
How do you determine how to collocate processes in a same container?
So right now we primarily use locality information to determine which task runs on a container. We aren't at a point where we say that on a one-to-one edge, for example, the producer produces some data on a container, the corresponding consumer task should just run on that container. We aren't there yet, but we plan to get there. That's where the affinity-based scheduling comes in. For now, it's fully locality-based. Okay, so in terms of reuse, the scheduler actually has a delay for locality. So the scheduler will not use a reused, an already available container immediately. It will wait some time for a container to become available or a local container to become available. It's not an immediate reuse. There is some delay for locality there. All right. Anything else or? Okay, thank you.